Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back. So let's continue with the different kind of lectures or compliant mechanisms. So today we will cover a new type of flexures, that is called hole flexures. So here you can see that if we can drill a hole, so for instance if we in either of the block, if you see if we drill a hole and then we just separate them out, so we create a sort of a hinge. So if we just for instance fix this part and apply a moment here, so it can flex easily. So there will be a hinge created here, so it can rotate, and it's widely used in precision machines because it can give us adjustment, and any small deviations we can easily correct using these kind of features. So, and since we create this kind of flexure using holes, so generally it's referred as hole flexures. So, for very small rotations, it's a very useful, and so for precision application where we are looking at like these kind of ranges below 1 degree, a kind of adjustment. So it's very effective, and we can do wire ADM, and we can create a slit, and we can create the holes here, and these are the sections. So H, these are quite important, the diameter. So this is the functional part in this case, and what we realize that not necessarily we have to create the entire hole, but then a section maybe more than 120 degrees is already good enough. So that alpha is important, and this thickness of the hinge, that is important. So if you look at it, what we realize, yes, there is a thickness also in the other dimension. So we can think of this like, so it's a clear from this CAD model, and what we realize that when we have this kind of flexures, so what are the things we are looking at? So for instance along X, so because of the orientation, what we can say that is the longitudinal direction, or is the perpendicular direction with respect to the holes created. So the in this case is the X direction. So this is my constraint direction, and phi is the rotation along X. So again, this is, if it's in 3 dimensions, so substantial thickness is there. So that will be again a constraint direction, both translation and rotation along X. If we talk about Y, so Y translation again is a stiff, so it's a constraint direction, but this is psi is something what we are looking at. So if we apply a moment of force, so create a moment along y direction, so y axis, so that because of that there will be rotation psi, and that is what we are looking at, that is the compliant direction. So that is the angle. When we look at z, so z again is a stiff direction, and theta as well. So because of the large thickness, the theta is also constrained. So if it's in 3 dimension, what we can easily say that we have only one dot, and that is psi, so rotation along y-axis, and that way we can create a hinge, so rotation axis. So these are the parameters, and what we will be interested in different kind of stiffness values, and what are the range of motions. And of course, we would also like to know what are the stress levels. So when it comes to dimensioning, yes, the parameter which will definitely of interest is sigma, so the stress values. And so yes, it's the same figure, and now we are talking about the rotation, this psi, and then the other stiffnesses value we will be talking about. So again, the 3D CAD helps us to visualize it well, and you can have a moment acting, and there will be a hinge. So psi. So this is what we are interested. What is the range of motion? And this is non-dimensional graph, and where all the parameters are plotted in one with respect to this non-dimensional parameters. So what we can see that yes, along y-axis you have different parameters, and along x-axis we have h by d, and or under root h by d is uh, space, but h by d is little it's not linear. So what we realize that yes, if we have this sigma, so if you want to know the sigma value, the stress value with respect to h by d, this is what we are interested in, this plot. So we'll be also interested in knowing that k values, the rotational stiffness in psi direction. So we may have to refer to this plot. And okay, so these are like a stiff direction, cx and cz directions, and we can also calculate the strain values. So knowing the stresses. So this is the chart we'll be using for any kind of dimensioning. This is, of course, is from the Professor Sumer's book, and this is widely used in Netherlands while designing all the machines for precision application, whether it's a ASML machine for lithography or for any kind of electronic or electrical machines which are moving at a very high speeds, and we want to maintain the accuracies. So these features will be embedded in the designs, and we have to dimension, we have to know what are the geometric parameters, the specification, the diameter of the hole or the thickness, the hinge h, all these parameters we have to calculate. And so yes, there are literature available, and we can always refer to that if it's required. These days we can also use different FE packages, and also can verify. But in order to get the initial calculations, we can use these graphs, these plots, to get those numbers. So for instance, if we have this example, and now yeah, though it's already given, but suppose this is the block, and there is a thickness, so it's also we can extend to the other dimensions, so which is not shown, but just the projection, the it's a given. So this is the T what we have, and yes, we drill the hole and then connect it, and we can get out of wire iridium this kind of features. So what happens if we apply force F, and we fix the bottom part, the top part, if we apply any kind of actuation. So this will be the excursion movement, that delta, it can move. if we try to look at it closely, what we realize that this is nothing but top and bottom we have, and corresponding to this, these are my hinge locations. So these are my hinge locations, and I can simply connect through a member, rigid member. So these are my hinge points, and if you look at it, this is what is important. Actually, these are the functional parts only. So, and of course the base and the top platform is there. The other sections, for instance, this part, many times we don't remove it, we just keep it there, and it works as a mechanical stop, because if there is a movement, yeah, after certain movement it will hit, and then it will so it's a thick mass, so it will work as a safety mechanism and mechanical stop, so it helps in STEM. But even if we remove these parts, suppose if we just machine it out, it will still work. So the functional part are the shaded part, and if suppose if we have to dimension it, so the application is okay if we have certain actuation force and the excursion, that a displacement is given, what is the range of motion we need. P is the length of the rigid section, what we can say, this is my P, length of that link. So what will be the diameter of the hole drilled, and the thickness, this H. So very good example, and one can also realize that for very small movement, it's a very effective solution, uh, elastic mechanism, so it can always come back. The precision, everything is we can achieve. So if we have to do that, how to proceed? So just one example, we just follow the same charts here. So this is the reference drawing, and if we start with this mechanism, and if we have to design, so suppose thickness is given, this is what is the excursion, the range of motion plus minus 0.5 mm is given. We apply a force, there is a displacement, that is what is given. The diameter, yeah, we can give or we can find. So some parameters we can assume, some we can find, or yeah, design is an iterative process. So some of the parameters in the beginning we may assume, and we can start. But suppose after calculation certain numbers we find that okay, uh, it hits the manufacturing limitations, then maybe we have to rework and find different ways. So yeah, for a given material, suppose that sigma max is given, so yeah, probably so SS. So sigma max is given, so what is allowable stress level? So considering all the safety factors and stress concentration, all those things. So suppose this number is given 400 MPa, megapascal, that is the sigma allowable, and this is the E value 210 GPa. So then how to arrive at the H, what should be the thickness? So if we have to start, but we realize that maybe since sigma and E is given, we can start with this one. What we have to also find is this psi value, the rotation. But the rotation, what will happen when it moves? Yeah, it may, when it moves to this location, so this point will shift. So So this is what psi is. So that is the maximum value. And what we also realize that since P is given, yeah, here P is also given. So P is nothing but your delta, for instance. So P is given. So it's a P times psi, and that will give the delta. So since delta is given, P is known, so we can calculate this sigma psi. So this the rotation will be nothing but that delta times P. Of course, it should be in radian, and that is the value we use it here. So sigma psi, I simply write 1, and then psi value is given E, and then we can calculate and we can get the number. So after putting all that number, we can find some number here. I don't know where, but okay, we can put the values, we can check, and suppose it's coming somewhere here. So I'm just guessing. So based on that sigma values, I can also find h by d. So h by d can be calculated here, or under root h by d, whichever we find convenient. Here we can find, and once h by d is given, h can be calculated as d is known. H is some number times d. So this will be known. So h. So what is h here? So if these dimensions are given, so here you can see r and r. So 2r is d plus h. Yeah, this is the, so this is how we locate. So yeah, certain dimension we call it s. So we can find, an h is known. If it doesn't, suppose this h is very small and maybe comes in microns, you know that it's not possible. Um, it's a difficult number to achieve. So maybe then we have to rework, or we may have to assume different d, or maybe the t we have to change, or p. So these are variables, design variables, and we can change. So once h is known and we arrive at that d by h by d number, we can calculate other things as well. So h by d, this is known, whatever h we select based on that. So remember, this is like limiting values. We can always go for a number which is safer than that, and accordingly this point can move also. So depending on what h parameter we are choosing. But yes, assuming that whatever h we have obtained, we proceed with that, we come here and we can calculate rotational stiffness, k psi, kappa or k, whatever you call it, the rotational stiffness we can get from here. So again, here all the parameters are known since h already obtained, and this number is also known, so we can find k. Once k is known, what we also realize that is the rotational stiffness of the hinge. And if I'm interested in knowing what is the k total, so when I'm applying a force, what is the stiffness felt at that point by the actuator? Then using the equations and equivalence, we can also find k total in terms of k psi. So yeah, I think all those things we have to check and apply and calculate. We can also use energy equations, we can use force balance equations, and we can obtain these numbers. So if we do that, what we realize maybe is possible to check, and what we realize that these numbers we can obtain easily. So for instance, so please check that. So one calculation from the calculation, h and f. So various steps I explained. So just follow those steps and you should be able to arrive at these numbers. If not, we can take up this problem again in detail. But yes, these numbers you have to be careful. I just assumed certain numbers and proceeded, but I already explained what are the various steps, and you should be arrive at these numbers. So one little here and there, because it's a plot, so you can always have some decimal error, and then you arrive at a different numbers, but that is fine. What is important is the process and how to attack the problem, and also understand the hidden mechanism. So whenever we are doing some problems, I think it's very important to understand what is the basic mechanism there. If we understand the kinematics, the dynamics, of course, we can always assume certain stiffnesses and proceed and can find different values. So other thing is, of course, is one axis, but what will be the orientation of the whole flexures? What are the guidelines? So I think as we learned when we are talking about the sheet flexures or simple cantilever structure, so similar things we will see here as well. So yeah, here h by d, one of the parameters, if we see here. So if that ratio, h by d ratio, is high, then what does it mean? It means the thickness is really high, and it means the stiffness in the CZ and CY direction will be equivalent, right? And so, but at the same time, the displacement might be very small as well. When we have a h by d ratio really small, then what happens? CZ in this direction, because this section is now lengthened, and what happens if there is a loading in the z direction, there will be shear, and because of that, what we will see that this stiffness will lose. So it will not work as a whole flexure, but more like a beam, and we have to be careful uh, in different kind of applications. Of course, this can be used if we know that the predominant force is along this direction, right? If the force is so it's very similar to the beam flexures what we covered earlier. So if it's long, then we have to be careful. So similar approach, if we know the direction of the force acting on it, so we can align this hinge along that. It means aligning hinge means the location of the hole will be in the perpendicular direction to that F. So that's what we mean by the orientation. So if we know that this is my dominant force, then the direction of the holes will be in the perpendicular plane. What we also know that if we are not very sure about that, then we can always have a arrangement, orthogonal arrangement, and that's what we have done here. So if there is a force here, so cross pivot structure we can do with the whole flexure. So in this case, we may not have to worry about that shear. So this is one and this is another one. So orthogonal direction, and so it's again a sandwich model. So we just split one of the sides into halves and put on the either side and get this sandwich structure and the symmetric design. So very good, and in this case this direction can change in any direction. We may not have to worry because one will take care of that load always. So we can always write the cos and sine, so we can resolve into two components and it can take care of that. So that's about the whole flexures, and we can look at some applications. So for instance, if we have this problem, So how to convert into some notch hinge mechanism, or call it hole flexures. So notch hinge is because notches we are creating, so that's why that name is there. So the problem statement is here. So it's a fix. This part is fixed, and the blue part has to be adjustable, and this is adjusted by this screw. So we can turn, and then we can apply a force here, so we can adjust the height. So, and the blue part has to also sustain an external load F. So yes, I think it looks very counterintuitive. If you remove the screw, what we realize that it looks a parallelogram mechanism, and simply if we put a load, it will just go down. But moment we put this screw, actually this is what limits it. So we can turn the screw, and yes, by virtue of that, this force will be supported. So if we have to change into a hole flexure design, we know that the hinges will be in these 4 locations. So actually it will be just nothing but this kind of mechanism with the hinges here. And again, now this part is more or less like, then we have through hole, and we can support here. So we can lock and then close it. But if we remove and we only look at this part, this look like just a mechanism what we discussed earlier, and one can easily make mistake of putting the hole hinges there with the same orientation. So one can find that, oh, it's a symmetric design, and we can go about that. But if we look at it closely, what we realize that the forces direction might be different. And what we also understand that if we know the direction of forces, then if it's not moving a lot and the dominant force direction is known and more or less is static, we can fix the orientation. So we have to understand that, and for getting the correct hinge orientation, so this is the problem we are talking about. So what is required is we have to do the force equilibrium. So write the forces. So what we realize, this is the two force member. If we take this, so direction is known. In that case, under equilibrium, there will be only this force, right? Either in tension or compression. So that force is known. So that's why you have this force is known. This is the three force member, this part. So one will be at this part, and then one here, one at the support hinge, and one external force also acting here. So based on that, we can also find out what we realize, that when we do the uh, make the free body diagram and write the force and moment equilibrium equations, we should be able to find it. And again, we find that there is a this force direction is more or less defined. So these two, and likewise, we can also get this force as well. So once we know the force direction, it's very easy after that. So this is the kind of governing uh, mechanism, what we can say. And once we know the forces, we can have to simply, we know the hinge location, so we place it there. So hinge location is known, right, from here. So from this figure, we know the hinge locations. But since forces, the force directions are known, we can just put a perpendicular line along that hinge, and then we can create the hole around that. So similarly here, And of course, we need to also know that uh, for the whole hinge or whole flexures, we have to also find what are the H values, right? So once the dimensions are known, we can find it, and ultimately we can arrive at this solution. And we can use so we can drill a hole with the diameter of the hole whatever we get, and then we connect through iridium, and then we can find this mechanism. So very good example to illustrate that. And yeah, we can also do some 3D printing, and I can show it's with the enlarged model we can always look at this problem. Similarly, there are many solutions in or many problems in optomechatronics applications, in photonics, right, where we want to open the slit with a very in a very controlled way. And for that kind of applications, can we design devices around it? So for any optical instrument, and suppose we want to have a symmetrical opening, so from here they should open symmetrically and with one actuation. So again, it's a very clever design. So we can, once the mechanism is known, it looks very easy, but one has to always think that, like, how to get that symmetric movement with one actuation. So parallel bar is there definitely, but then how to get it through one input? So because there are two inputs going, and because of that, the two sides, the one loop and two loop, the two loops getting similar input and then displacing. So by similar amount, so symmetrical with its bisector. So very good design. Yes, after some time they will behave differently, and the opening will not be symmetrical. But yes, if it's the range of motion is known, and if it works for that, then why not? So again, very good example, and how to implement it. So once the basic mechanism is known, if it's known, it's very easy to convert to the equivalent mechanism. So again, the hinge locations are there, but then orientation we have to calculate. So we have to do the dynamics. We have to write the equation, dynamic equation, and we have to find what are the direction of the forces. And accordingly, we can also find what will be the orientations. And this is again with the just one input here. So we can adjust the screw. Here you can see a spring for preloading. So it's a preloaded uh, against this screw, and once we adjust it, it will have that opening. So again, very good design, and one can always try with the 3D printing or even with the laser cutting. So one can use acrylic sheet and just make this model and try yourself. Very good model. What if you want to have a large motion? So in that case, it's a symmetrical design, and again with the one input here. So what you see here, you get this output. So symmetric movement, opening and closing, and since it's a symmetric, what you realize that you can achieve that for a large range of motion. What is also very nice here is this input here. What you realize that is passing through the center of compliance of these parallel mechanisms. So these are some salient features, and these are something which we learn in the course, but how to implement in the design, that takes a lot of effort and a lot of iterations, and one should always give credit to the designer who has come up with this kind of design in the first place. Yes, once it's there, it's very easy to analyze and do a lot of things around it. So again, very good design for photonics application. So there are various examples, and we'll learn, we will take up some problems later in the next lecture. And so whether it's controlling some devices, photonic application, or some mirror for a space applications, for radar application, or some for some kind of pointing devices, very good examples. And we know that using this method we can do a very small adjustment, so the resolution can be very high. We can achieve a very high resolution. Of course, if we are looking for a very targeted application, and suppose maybe looking for like arc second or arc minute kind of adjustment or resolution, these kind of elements are very important and it should be there. And yes, here we are talking about adjustment with the screws. It's just to illustrate, but if it has to be done in a very dynamic way and with a very high speed, then of course the screw can be replaced with some kind of actuators, piezo actuators, or any kind of other kind of linear actuators, depending on the application, depending on the payload. So we'll talk about different case studies, different kind of examples, and I think we should be able to appreciate the designs, what what we have here. But at the same time, we should be able to implement this concept in real application in our own designs, for whether it's for a space application or for any civilian applications, or even for fun. And suppose any kind of light or pointing devices we want to make or want to play with the lasers. And so like for instance in Eindhoven is the hub for Philips, and every year they have the for entire week they have light show throughout the city. And you can just walk around in the evening and you can see very nice projections all over the place. And so you can see very good examples of these kind of devices where you can just play with the laser on the wall, and in the night you can create different kind of uh, features. And kids will love to see that. But you can also convert into real application for engineering, and for semiconductor application, for electronic devices, for any kind of photonics application. So we'll cover more. We'll stop here today. Thank you.